Right. Now, up to the last week, we have talked, if you remember, we have started talking about the stars. And if I summarize what we did, we started with talking about different properties of the stars, such as the magnitude, brightness, temperature, and those kind of stuff, and different spectral classes that stars belongs to. Those are the things actually we have discussed so far. And then we moved on to talking about the formation of the stars, right? So what kind of conditions that a particular molecular cloud should satisfy in order to form new stars, right? So if you remember, we talked about these conditions and how a protostar will born, and then those kind of things, right? Like the genes criteria that should satisfy for the formation of stars. And then after a star is formed, then we discussed what kind of reactions that we have inside stars. For example, there are a lot of fusion reactions, right? Which is the primary method of generating energy inside the star, right? And based on the initial mass of the star, we talk that stars will end up at different places in their life, right? And for that, actually, just let me switch off my video now just to make you. And if you remember this particular diagram that I have talked most of the time, so this is the place where we started talking about molecular clouds. And from the molecular clouds, once a certain set of conditions are satisfied, and this is basically about the genes criteria, there will be protostars that are born. And from the protostars, basically these newborn stars are mostly in these open star clusters, which is what we talked, I guess, in the last time when we met. And once you have a protostar, depending on the initial mass of the protostar, we can divide the evolutionary phases into three categories. The first one is the brown dwarf, which means that there is not enough energy to generate to convert hydrogen into helium from fusion reactions, and because of that, those type of stars will stop evolving straight away and will stay as brown dwarfs. And we usually used to tell that these kind of stars as failed stars, right? And then for the low mass stars, so that means if the mass of a particular star is less than the 8 times of the mass of the sun, then those stars has a different evolutionary mechanism compared to these high mass stars, right? Now, what we have basically, what we will be talking today is about this evolutionary phase. Basically, what will happen to low mass stars, and even in that case, there is another possibility of having a type 1A supernova, right? And this part we will discuss separately. And basically, we will first pay our attention about this section right here in this first presentation. And if the time permits, we will also talk about what will happen to these high mass stars. And for the high mass stars, there is a phase that you will have a supernova explosion as well right here, right? After that, you will have maybe a planetary nebula and maybe a black hole or neutron star after that. So we will go into those phases separately, right? Right. Now, when you talk about the death of stars, so basically we have been discussing about the birth of a star and what happens inside the star, those kind of stuff, right? Now, from today on, we are actually talking about the death of stars, how a star will die at the end, right? Now, if you remember the main sequence of stars, I am basically referring to the HR diagram, right? Which we have been, used quite a lot to explain different types of phenomena. Now, all main sequence of stars, eventually will evolve off the main sequence and become giant stars. That is obvious, no? So this one we have discussed, right? All these main sequence stars, which means the stars which are on the main sequence line, at one day they will evolve into different phases and will go off the main sequence star into different locations of the HR diagram, right? Now, what happens to these stars after they spend their time in the main sequence will mainly based on this star's mass, right? And if we talk about in terms of the masses, stars with masses less than the mass of the sun. So that means 8 solar masses. Actually, here the solar mass should have this symbol right here. So for some reason it is not printed correctly. So make that correction yourself, right? So the stars with masses less than the mass of 8 times the mass of the sun or 8 solar masses, they will never be able to burn carbon in their cores. Now, if you remember the central region of a star, you have hydrogen and helium initially. Initially, what will happen is hydrogen will burn into helium, and then you have helium, and then also the helium will start burning and will become carbon, right? So that is what will happen, right? Now, for these, when you have these low mass stars, they are actually, these stars are not capable of burn carbon in their cores, right? So what will happen is the stars that couldn't burn carbon in their cores, we will normally refer those kind of stars as low mass stars, right? And basically one solar mass is, from this symbol once again, should be 2 times 10 to the power 30 kilograms. Basically, these type of stars, which are less than 8 times the mass of the sun. So that means this also includes our sun itself as well, right? So those type of stars are referred as low mass stars, while the other type of stars where the main sequence mass is greater than the 8 times the mass of the sun or the 8 solar masses, so these heavy stars are capable of burn carbon into other heavy elements, right? Actually, the reason is obvious because once you have a higher mass, those masses can convert, once the mass is higher, the gravity is higher. So the gravitational pull towards the central region will higher, which will provide high enough temperatures to burn even heavy elements. So that is the secret, right? So this is why high mass stars are capable of burning heavy elements, while low mass stars will stop at the point where they have to burn carbon in their cores, right? Right. Now, what happens is in this, so let's first talk about the low mass stars. So now you should understand what low mass stars means and what high mass stars means, right? So basically it is so this division came from the mechanism that they have inside in terms of converting energy, converting hydrogen into different heavy materials, right? Now, you know that for these low mass stars, when this helium fusion, that means when helium fusion ceases, that means when helium stops burning and making carbon, this core of these low mass stars will have a non-burning carbon ash, because once when helium fusion finishes, what you have is carbon, right? So for these low mass stars, you will have some carbon ash at the center, right? Now this carbon ash we consider as a non-burning core, and this carbon core will start to collapse. So that is basically because you do not have enough uh, mass for the star to create higher temperatures to burn carbon into other heavy metals, and because that these fusion reactions will stop at this particular stage for these low mass stars. And so as a result of that, you are not creating enough temperature at the central region because you do not have any fusion reactions going on. So that means this you cannot actually, the star itself cannot balance the gravity, because gravity is always an attractive force. It continues to attract everything, and so that force will never stop, right? But the problem here now is this attraction force. To counterattack for this attraction force, there is nothing in the central region, because you are not burning this carbon ash into heavy metals, which is a fusion reaction that can generate a lot of energy to compete with the gravity. But that doesn't happen in these type of low mass stars. And so what will happen is this collapse of the material due to the gravity will leads to increasing central temperatures again, right? So this once since there is nothing that you can stop this gravity, so the gravity continues to collapse all the materials, and as a result of that, this outer shell, if you remember, there is a shell that goes around the central region. So this outer shell is a helium shell, and it will start burning helium. Meanwhile, there is another shell in the most outer region, which is a hydrogen shell. So that is continue to burn as well, right? Now, as a result of this complete process, the outer angle of the star will expand to compensate for that, right? And in this particular stage, we used to tell that the star is now a supergiant, right? So this is what we called as a supergiant. So you can see that there is carbon-oxygen core at the central region, and there is a hydrogen fusion shell. And after that, there is a hydrogen fusing shell. Sorry, this is a helium one, right? So that this is what I have been talking. Central region, it doesn't create enough temperature because of the low mass. It cannot support these higher temperatures, and no reactions will go in at the central region. As a result of that, all the materials will be collapsed towards the central region because of the gravity. And once this happens, the temperature will increase in the central region, which will affect for this helium shell and for the hydrogen fusing shell, right? So that's what happens. Now, as a result of that, these two outer shells will get expanded, and because of that, the size of the star will increase, right? Because these outer shells, when they get expanded, the size will increase automatically, and this increase of the size will lead to increase in the luminosity, right? Remember that I have discussed with you that there are two main factors affecting for the luminosity or the brightness of a star. Number one is temperature, and the number two is surface area. Now here, since the stars get larger and larger, the surface area increases. As a result of that, the luminosity is increasing, right? Now this will cause a vertical rise of the HR diagram. So so the reason is actually, if this is the HR diagram, you can see this is the vertical rise, right? So that basically happens due to the fact that there is nothing much change in the temperature, which is one factor that will affect the change in the luminosity. However, while keeping around the same temperature, it has increased its surface area or the size. And as a result of that, without changing much temperatures for this direction, it will increase its luminosity just purely because of the size of the star, right? So that's what happens in this particular phase, and that increase in the brightness of a star without having much effect from the temperature. So that means there will be no change in temperature in this direction, but the luminosity will increase like that, basically because of the size of the star has increased. And this path is what we called as the asymptotic giant branch. If you look at these three diagrams. Here, this third one, you can see the luminosity has increased rapidly, and that is what we called as the asymptotic giant branch. Now, what happens is now the star get more and more expanded, and after a few million years, this star's outer region is automatically ejected into the space because now the star has become very large. So the connection between the central region and the outer region of the star is, is minimal in this kind of situations. So what we have is, so there will be two distinctive components now in the stars. The number one is the expanding envelope, which is relatively cool, thin gases. So that is the outer region. It's like an envelope, right? So when you say an envelope, what is the possibility is this particular part can go away at any time because it's a one distinct feature of the star. And then you have that small dense core at the central region, right? And this core is mainly made of carbon ash, if you remember. And you can see there are two main components in this low mass stars in this particular situation. One is the expanding envelope, which is the outer region, and the second one is the small dense core. So those are the two main parts that you have inside these stars, especially in the low mass stars. Now there is a specific name for this the star, this particular stage with these two parts right here. So this type of objects are used to call as planetary nebulas, where you can clearly identify these two regions, small dense core and an expanding envelope kind of thing, right? And here is an example for this, few examples for these type of stars where you have the planetary nebula. You can clearly see that the central dense core is right here, and then you have this outer region very easily visible. This is the spirograph nebula. All of them are actually planetary nebulas. I'm just showing some pictures to give you a feeling about the description we had in terms of its shapes. You can clearly see the central region is right here, and then you have a large envelope, right? This is called cat's eye nebula. And once again, I am back for the HR diagram. So I'm just showing it from time to time just to give you an idea and just to remind you what we are talking about, right? Now in this HR diagram, you can see that here is the main sequence stars, and some of the stars have gone outside from the main sequence, and some of them are in this path, and some of them are in this path. So we are going to basically investigate this path up to here. Right. Now, in the last slide, we talk about the planetary nebulas. Now, what happens is when this planetary nebulas ages, which means after so long time, the surrounding shells of gas that you have in this planetary nebula, that is one part of the nebula, will eventually disperse and disappear from our view. So you will not see that outer part after some time. So only that you will have is the core of the star, which is mainly consists from carbon, right? Now this particular object that is remaining after planetary nebula is escaped away is what we called as the white dwarf, right? Now, these white dwarfs are actually very different from ordinary stars because they are not undergoing fusion in their cores. They're not doing any fusion reactions. And because of that, these kind of stars have shrunk into very dense objects because, when you do not have any kind of fusion reactions in the central region, there is not much heat will be generated. And because of that, due to the gravity, everything will be collapsed towards the central region. So that's why you will have very dense objects as white dwarfs, right? So if you compare it, they are typically about 100 times smaller than the sun. So it is that much smaller, right? So these are very dense objects. Now the other question is, now we told that in the central region there is not much fusion reactions going on, because the amount of material that you have at the central region of the star in these low mass stars are not enough to create enough central temperatures to have these higher, I mean, to have these heavy metals burn, right? And because of that, uh, you will have, you actually do not have any kind of fusion reactions going on in the central region of these white dwarfs. Then we should have a question that how these stars are balanced, because there should at some point there should be some kind of force that comes from internally towards the outer region which can balance the gravity, right? So otherwise the star will use to collapse forever due to the gravity, but that's not happened. Actually that happens at a one particular type, so which is what we will call as black holes, and we will learn about that in future, especially for the high mass stars. But in this particular case, when everything is very densely packed, there is something called electron pressure, because when everything is densely packed, electrons are similar kind of uh, molecules or particles, so which means they will repel each other, and this particular phenomena will make a new electron pressure, right? And from this electron pressure, you can stop the gravity or balance the gravity, right? And we also call this as electron degenerate pressure, which means not the same type of electrons in terms they are, I mean the charges. So they are same kind of in they have electrons. So these electrons can create this electron degenerate pressure because they are also repelling each other, no? And once you have this electron degenerate pressure, that can balance the gravity, right? Now, uh, this is how a white dwarf is balanced in the sky, right? Uh, Actually, what will happen is as white dwarfs are also ages, then they gradually cool off and fade, producing a white dwarf sequence on the HR diagram. So this is what will happen in the HR diagram. You will see a sequence of white dwarfs, right? Now, in this particular uh, diagram, you can see a complete evolutionary process for a low mass star, which is pretty much close to a star like our sun, right? You can see that start from A, the giant phase, and go in this path and will become a white dwarf around here, right? So if you read through this paragraph that I have here, you will probably understand it clearly. So I'm not explaining you each and every part. Right. Now, this is actually a visible light and X-ray images of two of the Sirius star system. And you probably do not know that the Sirius is actually a double star system. There are two stars there, Sirius A and B. But for the naked eye, it's hard to, uh, identify those. Even from the Hubble Space Telescope, this is how you see it. So there is one of those stars, there is smaller, and there is the other star. Now, if you want to look at this particular star, you have to go for a different wavelength, right? So that's what they have done here. Using X-ray wavelength, you can see that this is very bright in X-rays. This is not that much. So this is the star. It was here, right? But in X-ray regions, it is the more brighter one. Here are some examples of having white dwarfs. Right? Right. So this is basically what happens to a low mass star. Right. So once again, we started from here and talked about the different phases of the stars. And then I told you that this is basically we actually talked about brown dwarfs. And then this is what we have talked today, become a planetary nebula and become a white dwarf. Okay? Apart from that, there is a possibility after the planetary nebula, once you have a white dwarf, it could once have a white dwarf and a companion star, that could actually lead to a type 1A supernova, right? So that's what you see here, type 1A supernova. The nova is also a possibility, but astronomers have a very special interest about type 1A supernova for a reason that you will understand when you talk about measuring distances to galaxies. Right, so I guess so this is what I wanted to explain for today. I think I will be stopping today a little bit earlier. That's basically because we have finished this section about the death of low mass stars. So this is eventually what would happen to a low mass star, right? So since we have not been, meeting regularly for some time, I just need to fresh up your knowledge, just remind what we have been doing and just do a small section today, just for you to get into the lectures again, right? And because of that, I'm not going to continue furthermore from here. So we just keep it as a half an hour lecture today, right? Now from the next day, we will have like 8 1 hour lectures, probably let's say 2 per week or something like that. So not that much, but just make sure that you go through the previous notes. I think all the notes are available in the Google Classroom. Maybe the last 1 or 2 video lectures may not be available, but I will make them available as well. So go through the lecture notes, and try to understand what we have been talking about. And on the next day, because the death of high mass stars, there are a lot of few more things to talk about, and because of that, may take some time, and because of that, I will not start it today. So make sure that you go through this death of low mass stars and take a good understanding about it, right? So then it will be very helpful for us to go through the next 2 or 3 lectures, which is about death of high mass stars, neutron stars, and black holes, right? Before we move on to galaxies, right? Now, anybody have any questions from this section? Actually, you will see that I am trying to keep it as much shorter as possible since we are doing it online, right? But sometimes I may have to go for 1 hour and a half, 1.5 hour if time needed. Other than that, I would like to go with like these kind of shorter sessions. Right, so if you do not have questions, the next day I will meet with you to discuss about the death of high mass stars, which will be a lecture about an hour, right? And that lecture could come up anytime around, Wednesday or Thursday in this week, right? I will update you. Anybody have any questions once again? Right, so it seems that you do not have any questions, or maybe you kind of forget what we have done, right? Because we didn't do lectures for 3 weeks. So just go and remind, brush up your the knowledge and revise what we have done, including this set of lectures, so that it will be much easier for you to follow the next series of lectures, right? So because of that, I'm going to stop here. Few reasons. One thing is obviously we are done with this section, and the other thing is I feel that it may be better for you to go and revise a little bit before we, rush through the other lectures, right? So I will just give you a few days to, revise what we have done up to here, right? And then we will move on from that. And the next lecture is most probably on somewhere between, after Wednesday. Let's keep it in that way, right? So you'll have a few days to, revise what you have done, and you can come up with any kind of questions that if you need answers, even from the previous set of lectures, right? Any questions? Right. So if you do not have questions, let me stop from here. And good night to everyone. And we will move again for our next complete lecture. We will meet at some point in the same week. Right. Right. Thank you so much.